Modern mathematics curriculum traces the origin of probability theory to a single year, 1654. That summer, Blaise Pascal and Pierre de Fermat exchanged a series of letters to solve the problem of points, a dispute over how to divide stakes in an unfinished gambling match. Historians of science routinely point to this correspondence as the genesis of mathematical chance. Earlier texts mentioning dice or wagers are categorized as gamblers' manuals that lack theoretical rigor. That timeline ignores an Italian polymath named Girolamo Cardano. Cardano authored Liber de Ludo alle, the book on games of chance, around 1520, completely outdating the French mathematicians. The foundational architecture of probability, including defining sample spaces and combinatorial limits, was mapped out 134 years before Pascal and Fermat began their correspondence. In the early 1520s, Cardano was a student rector at the University of Padua. He was a brilliant, mathematically trained physician and a compulsive gambler who routinely wagered high stakes. The games of chance on his table utilized specific physical geometries, primarily four-sided animal knucklebones called astragals, and standard six-sided dice known as tesserae. To survive mounting debts at the gaming tables, Cardano required a reliable system. Superstition and luck were insufficient. He needed logic derived entirely from physical symmetry. In Chapter 6 of his manuscript, he formalizes his fundamental principle of gambling. He states that fair play relies strictly on equal conditions of the opponents, the money, the dice box, and the die itself. By assuming a perfectly symmetric physical environment, Cardano crossed the bridge from observing gambling trends to defining pure mathematical axioms. This diagram illustrates Cardano's terminology. He used the word circuit to describe the total possible outcomes of a system. The circuit is the direct mathematical equivalent of what we now call the sample space. He then defines equality. In a perfectly symmetric system, equality is the baseline mathematical expectation, which he frames as exactly 1/2 of the circuit. In Chapter 11, he proves this by mapping the combinatorics of two six-sided dice. He calculates the remaining outcomes by identifying 15 pairs of unlike faces, such as a 1 and a 2. Cardano recognizes that these 15 combinations must be doubled to account for the physical sequence of the dice falling. A 1-2 is distinct from a 2-1. That yields 30 unlike permutations. Summing the 6 doublets and the 30 permutations proves the total two-dice circuit is exactly 36. From this circuit, he deduces the exact equality is 18. He further isolates specific odds, noting that the chance of rolling at least one ace occurs exactly 11 times out of the 36. Distinguishing between combinations and permutations without modern algebraic formulas is an act of strict mathematical deduction, separating his manuscript from a simple betting guide. In Chapter 12, Cardano scales his logic to the game of Fritilis, testing his system against the exponential complexity of 3 dice. He deduces the precise limit for this three-dimensional circuit, 216 total outcomes. He builds this by identifying the 6 triplet combinations, where all 3 faces match. Next, he isolates the doublet and odd throws. He calculates 30 base variations, multiplies them by 3 positional permutations, yielding 90 outcomes. Finally, he charts the throws with 3 unlike faces. 20 base combinations multiplied by 6 permutations yield 120 outcomes. He sums the 6 triplets, the 90 doublets, and the 120 unlike permutations. The total perfectly matches the circuit of 216. Using this exhaustive model, he deduces that a single chosen face will appear exactly 108 times within the entire 3-dice circuit. Accurately mapping a 216 outcome sample space using only prose logic requires immense abstraction. Cardano completed this in the 1520s. Chapters 14 and 15 present his ultimate mathematical test, calculating the odds of an event occurring across multiple successive throws. Cardano poses a specific challenge. What are the exact wagers required if a player bets on rolling an ace, a deuce, or a tray across 3 successive casts of 2 dice? This equation establishes the baseline data for a single throw. Out of a circuit of 36, there are 27 favorable outcomes for this bet. To calculate the successive odds, his first operation is to multiply the total circuit into itself 3 times. 36 cubed yields a total successive sample space of 46,656. His second operation is to cube the favorable outcomes. 27 cubed yields 19,683 favorable successive outcomes. Cardano warns against using only these 2 numbers to determine final odds, pointing out a common calculation error made by other scholars of his time. His correct final operation requires subtracting the favorable outcomes from the total circuit to find the exact number of failing outcomes, 26,973. He displays his final ratio by comparing the remainder to the favorable outcomes. The mathematically perfect odds dictate a wager of roughly 1.37 to 1. This proof demonstrates that Cardano had fully mastered the multiplicative rule for independent events, entirely circumventing the need for modern exponent notation. Despite these perfect derivations, Cardano recognized an inherent flaw when applying theoretical probability to real life. In Chapter 15, he highlights the vast discrepancy between an isolated physical event and an infinite timeline, writing, "The magnitude of the circuit is the length of time which shows forth all forms." This single sentence is an early, perfectly articulated definition of the law of large numbers. Because gamblers do not operate on an infinite timeline, short-term physical variance dictates the outcome of the game. He became obsessed with the physical variables that could skew the circuit, tracking minute details like the slope of the table or the specific angle of a hanging dice box. He devotes extensive sections to warning players about asymmetric, rounded, or fraudulently weighted dice that disrupt the baseline equality. Cardano understood a reality that purely theoretical mathematicians often miss. A mathematical model is fragile, easily corrupted by the physics of the real world. While Pascal and Fermat corresponded within the academic security of the French aristocracy, Cardano's proofs were forged by the life-or-death necessity of the gambler. The 1654 letters successfully refined probability theory and integrated it into the academic establishment. Cardano's historical erasure stems from a logistical delay. Liber de Ludo Alii remained lost and unpublished until 1663, decades after his death, and 9 years after Pascal and Fermat's letters circulated. Yet the core technical takeaways, sample spaces, expected value, and the calculation of independent permutations belong firmly to Cardano. The modern science of risk rests on the gritty 16th century derivations of an Italian polymath who needed math to survive the gambling table.